probably curl up and die,
All my
right?
days, though.
I mean, what would you do if you didn't have this class to keep you busy? Good. Okay. Let's go ahead and get started. So what I want to do today is I want to continue with our discussion of how we impose the symmetries of special relativity in quantum field theory. So I'm going to complete our sort of discussion of general features of the symmetries of special relativity before, hopefully by the end of class today, using these considerations to construct the Dirac equation, which is the equation of motion of a spinner, a spin 1/2 particle, in a relativistic theory. So the symmetries of special relativity, as we learned last time, are known as the Poincare symmetries. Which can be regarded as changes of coordinates on Minkowski space or on 3 space and 1 time dimensional space-time. And they're generated by the following generators of the infinitesimal translations and Lorentz transformations. So here P mu is the generator of translations. So the generator of translations is d by dx mu. And the generator of Lorentz transformations is a differential operator that generalizes the differential operator x d by dy minus y d by dx that generates a rotation about the z-axis. So here I've written the 4 translation generators and the 6 Lorentz generators as differential operators. And these symmetries act both on classical fields as well as on the quantum Hilbert space. So when you think about the consequences of these symmetries in field theory, you should think really both about how these symmetries act on the classical physics, so the fields that describe the classical dynamics of your system, as well as on the quantum mechanical Hilbert space. So, for example, on a scalar field, phi, and here I suppose I should say on a classical scalar field, so we have a scalar field phi of x. A translation can be found just by exponentiating the generator of translations. So, for example, if you want to describe a translation by some vector a, so you want to translate the coordinate x mu to x mu plus a mu, then you would define so the translation operator, which would be e to the I a mu p mu. And what does that do? That takes phi at x and translates it to phi at x plus a. And in particular, if you just stare at that differential operator for a second, and you imagine exponentiating it to write e to the I a times p, and then multiply it times a function phi of x, what does it do? Well, it takes phi of x and moves it to phi of x plus a. Okay. So is that clear? I mean, if you think about expanding out that exponential, so that e to the I a mu p mu phi of x, what is that? Well, that's phi of x plus a mu d by dx mu phi of x plus a mu, a nu, d mu, d nu, phi of x plus dot, 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 which is otherwise known as the Taylor expansion for phi of x plus a. So that's the sense in which we say that these differential operators, d by dx mu, generate the translations in the x mu direction. So this is something probably that you've already seen before, but you may not have seen it in precisely this language. This is literally why the momentum operator in quantum mechanics is d by dx mu. It's because it's the generator of translations that take, x to x plus a constant. Similarly, a Lorentz transformation is characterized by a set of 6 numbers that we might call omega mu nu. And a finite Lorentz transformation is given by omega mu nu j mu nu, where we're using the Einstein summation notation to contract the mu and nu indices. And that will take phi at a point x to phi at lambda x, where I'm sort of, to keep the notation compact, not writing out all of the indices on, so on x here. So this is something like lambda mu nu x nu, otherwise known as the action of the matrix lambda on the x coordinates. And one of the things that you can show, and I think I probably am asking you to show on the next problem set, is just to verify for yourselves that when you exponentiate one of these Lorentz generators, regarded as a differential operator, you really do get the expected Lorentz transformation. Okay. So in the same way that when you exponentiate e to the I x d by dy minus y d by dx, acting on some function of x and y, all that does is that rotates rotates the x into the y coordinates, in the same way that when you exponentiate a d by dx, that gives you a translation of the x coordinate. So this is the sense in which we can regard the infinitesimal generators of the Poincare symmetries as differential operators acting on the coordinates. Okay. So here I've written down the manner in which these Lorentz transformations and translations act on a scalar field, but more generally, on a field, so on some other field, which we might denote phi, capital Phi. So phi, under a Lorentz transformation, will go to m times phi we hear now phi is not just one number, but rather a collection of numbers that I'm imagining arranging into a column vector, and m is some matrix that acts on that column vector, which depends on your Lorentz transformation. So in the case of a scalar field, it's just a number, and m is 1, okay? But in the case of a vector field, phi would be a 4-component object, a 4 vector, and m would be the Lorentz matrix. And in general, these m's have to satisfy the same group multiplication law as the Lorentz group. And the goal then is to try and construct a family of m's and a family of fields that transform nicely in the correct way under these Lorentz transformations. Okay. So to find a set of these m's that obey the group multiplication law, so m of lambda 1 times lambda 2 is m of lambda 1 times m of lambda 2. The way that we proceed is we first find a set of generators, so let's call them S mu nu, which obey the same algebra, that is to say, the same commutation relations. as the generators of the Lorentz group that we described above. And we then take m of lambda to be e to the I omega mu nu s mu nu. Okay. So, for example, if you wanted to write down the 4-vector representation of the Poincare group to describe a electromagnetic potential, say, what you would do is you would take those s mu nus to be the 4x4 matrices that I constructed for you last class, whose entries were either 1 or -1. Then you would exponentiate them, and that would just give you the 4x4 matrix lambda that would act on a 4-vector. But we're now trying to generalize this by finding other sorts of vector spaces and other sorts of operators on that vector space that will obey the correct group multiplication law. So this is hopefully more or less familiar to you in quantum mechanics. In quantum mechanics, you did exactly the same thing when you constructed, say, the spin 1/2, the Hilbert space of a spin 1/2 particle. What's the Hilbert space of a spin 1/2 particle? Well, you take the rotation generators, which you could first think of as differential operators that act on, the XYZ three-dimensional Euclidean space. And then you could look at the algebra obeyed by those J's, and then you could try and find a Hilbert space where there are other operators that obey the same algebra as the J's. And then that would be the Hilbert space that describes a particle with some spin. In the spin 1/2 case, it's a two-dimensional Hilbert space, and the J's are given by the Pauli matrices. And a finite rotation would be then found by exponentiating one of those Pauli matrices. So, for example, a rotation around the z-axis is given by e to the I theta, some angle, times sigma 3, when you view that as acting on the Hilbert space of a spin 1/2 particle. We now just want to generalize that to other sorts of systems. So our goal, which we will hopefully do by the end of the class today, is to find other sorts of spaces on which we can do this. So we will find some new sorts of S mu nus. So is the strategy clear here? I mean, it's a strategy that you've used before, for example, in the study of rotation in quantum mechanics. But when you learned quantum mechanics for the first time, you were learning so many new things that you probably didn't quite appreciate that this is exactly what you were doing. In fact, it's probably worth stepping back a second before I proceed to construct the Dirac equation and talk a little bit more generally about what's going on here. Okay. So far I've described the action of these symmetry generators on the classical fields phi, that is to say on the classical degrees of freedom. But when we consider the quantum theory, the symmetries will also have to act as the symmetries will also have to act on the quantum mechanical Hilbert space. And a symmetry acts on a quantum mechanical Hilbert space as a set of unitary operators. Remember that the definition of a symmetry in quantum mechanics is that it's a unitary operator that commutes with the Hamiltonian. So, for example, if you have a free particle whose Hamiltonian is p squared, let's just say p squared for a free particle, that Hamiltonian commutes with p, which is the generator of translations in the x direction, which means that the unitary operator e to the I ap is the unitary operator that generates a translation by an amount a acting on the quantum Hilbert space. So we say then that in quantum mechanics, the group of symmetries are represented by unitary operators, or we'd simply say maybe let me say that a little bit differently. We say that the Hilbert space is a so-called unitary representation of the symmetry group. So that's the mathematical language for symmetries in quantum mechanics. And here, the use of the word unitary representation, maybe I should just describe that for a second. So when we say a representation of a group, well, what is a group? A group is a set of elements that have a multiplication law. And a representation of some group. What is a representation? Well, it's a vector space or a Hilbert space. For our purposes, there's not much distinction between them, so let's call it H. And a map from the group, a map associated with each element of that group, which respects the group multiplication law. So that's the definition of a representation. And a unitary representation is just one where the m's are all unitary operators. So to say that in very practical language, if you have a group, say the rotation group or the Poincare group or any other group of symmetries, then if you want to describe a quantum mechanical system that has those symmetries, what do? You find a Hilbert space and a set of operators that obey that correct group multiplication law. Is that all more or less clear? I mean, the reason why I'm going through this in some detail is that, perhaps the most powerful principle in physics is the notion that if you want to describe some new system, you start by either understanding or making a guess for the symmetries of the system, and then you write down the most general dynamics that you can that are consistent with those symmetries. And this is the recipe for doing that in quantum mechanics. I mean, this is so, for example, as I'll describe to you in just a second, this will allow us to classify all possible kinds of particles that you can have in quantum field theory. This applies equally well in condensed matter physics. One of the favorite ways for people to proceed when they're studying materials physics, that if there's some material you don't understand, you postulate that there's some strange symmetry, and then you start writing down dynamics that are consistent with that symmetry. So let's just see this explicitly in an example that you already know. Okay. So let's take as an example the Hilbert space of a real scalar field. So what is that Hilbert space? Well, remember, it contained a vacuum state with no particles. It contained one particle states that are labeled by their momentum k. It contained two particle states labeled by momenta k1 and k2, and so on and so forth. How do the translations act? So that translation generator T of A that I wrote down before, that's no longer generated by a differential operator, but rather by a unitary operator on your Hilbert space. So we could call that U of TA if we want. And how does that act on one of these states? Well, it acts trivially on the vacuum state. That's the statement that the vacuum is translation invariant. But if you have a particle with momentum k and you perform a translation, you just multiply by a phase factor that is proportional to k mu times your translation vector a mu. So this is just the statement that if you have a momentum eigenstate and you do a translation, you multiply by a phase. Similarly, if you have some more complicated Lorentz transformation, a rotation or a boost, then that on the Hilbert space is represented by a unitary operator. And what does it do? Well, you just construct the 4-vector k mu that describes the energy momentum of that particle, and you act on it with lambda just like how you always act with a 4-vector. When we constructed the Hilbert space and the Fock space of our free scalar field, we wrote down explicitly the translation generators. Remember, we wrote down the Hamiltonian and the momentum generators. We didn't actually go through and write down the generators of these other Lorentz transformations, but we certainly could have. And probably, maybe that's an exercise that I'll have you guys do at some point. So that's how the single particle states transform. The two particle states transform in a similar way. So for example, let's say you have a state with particles of momentum k1 and k2, then that will go to lambda times k1 and lambda times k2. So you just act separately on, if you have two particles, one with momentum k1 and one with momentum k2, you do a rotation, then you just rotate the momentum of the particles simultaneously. Or if you want to think about this as a matrix, you could imagine, this is not necessarily the most convenient way of thinking about it, but if you imagined writing these as a matrix, then in terms of some matrix, U would just be given by the action of some block diagonal acting on that set of 4 vectors. I bring this up because there's another notation, or a piece of language that I'd like to introduce, which is that a representation which, by a change of basis, can be made block diagonal in the sense that all of the matrices M up here are block diagonal, is known as reducible, and otherwise it's irreducible. And the claim, or we could also call this a definition, is that a particle is an irreducible representation of the Poincare group. I guess we should say a unitary irreducible representation of the Poincare group. This, in a kind of mathematical language, is exactly what we mean by a particle. So, for example, we saw that the scalar field is a Hilbert space whose basis, say, of single particle states are given by an irreducible representation of the Poincare group, which has 1 degree of freedom per momentum mode. But in this course, we will encounter other particles which will be described by more complicated actions of the Poincare group. So just to sort of anticipate, when we describe a photon, the Hilbert space will have a basis that is labeled not just by a momentum mode, but also by a polarization. And the Lorentz group and the translation generators will act on this basis in some way. Okay. In particular, as you can probably anticipate, because I've drawn a vector symbol over the polarization symbol, what happens if you took a photon that's traveling in this direction, which has a particular polarization? Well, if you do a rotation on that, then the direction of propagation of the photon will rotate, and the polarization vector of the photon will rotate in the usual way. And so this is a theory where you don't have 1 degree of freedom per momentum mode, but in fact you have 2, because there are 2 possible polarizations of a photon, 2 possible polarizations of an electromagnetic wave. You probably saw this in your class on electromagnetism. You can either call them, so if you have a photon that's propagating, say, in the z direction, then they would be either x or y polarization, or sometimes you use a basis where they're either sort of circular clockwise or anti-clockwise polarization. So this would be a theory where you have 2 degrees of freedom per momentum mode. So why am I introducing this sort of fancy mathematical language? Well, the reason why I'm introducing this is because there's a remarkable result, which is in fact a mathematical theorem. So there's a theorem by Wigner which classifies all possible representations of the Poincare group. So there's a classification of any kind of possible particle you can have in a theory of quantum mechanics that's consistent with special relativity. I'm not going to prove this theorem. I'm not even really going to talk about it too much more in this class. But it is an incredibly powerful result, and it has, once I sort of write it down, it'll have a sort of clear physical interpretation for you. And the result is that the unitary irreducible representations of the Poincare group are labeled by 2 pieces of data. There are 2 numbers that label the possible irreducible representations of the Poincare group. One of them is a positive number, so I'll call it m squared. And the other of which is a half integer, and I'll call it j. So it's either 0, 1/2, 1, 3/2, so on and so forth. Such that at fixed momentum, there are 2j plus 1 degrees of freedom if m squared is positive, and 2 degrees of freedom if m squared is equal to 0. Okay. So that's the result. I'm actually lying here slightly. There are also actually plus other representations which are apparently not realized in nature. Which of course doesn't stop people from writing papers about them. But as far as you're concerned, that's it. Okay. Every possible particle that you will ever see in the world appears on this list somewhere. For example, the scalar that we have constructed so far in this class has an m squared, that was positive, and a spin j equals to 0. And the photon has m squared equals to 0, because photons are massless. And they have 2 degrees of freedom. But, there are other possibilities. So, for example, a graviton So a photon had m squared equals to 0 and j is equal to 1. And there are 2 degrees of freedom corresponding to the 2 polarizations of the photon. A graviton, for example, which would be the particle that you get if you quantize the fluctuations of the metric of spacetime, is massless because gravity is a long-range force, just like electromagnetism, and it has j is equal to 2. And you can already now tell me how many degrees of freedom a graviton has. You could just, from this theorem, you know that there are 2 possible polarizations for a graviton. Similarly, all of the particles of the Standard Model fall on this list as well. The electron, so the Higgs, for example, is a scalar field. The electrons, muons, quarks, all of these guys, gluons, they all fall on this list somewhere. So you can see here that the principle by which one can determine the possible physics of a theory just by studying its symmetries is a very powerful one. And if you're studying a theory with other symmetries, if you're looking at a materials physics system where you have, say, a 2D electron gas or something like that, then you would have other sorts of lists of the possible particles that you could have. So what I want to do now, however, is sort of dispense with this somewhat more mathematical discussion of representation theory and get down to the nitty-gritty and actually start constructing these theories. Maybe before I do so, I should pause and see if there are any questions. Yes?
So here, M is actually the mass?
M is the mass.
Okay.
Yes?
How many degrees of freedom does the graviton have?
2. Yes. So for example, they're called you don't call them X and Y polarization. They call them cross and X polarization. But you have to take a class on general relativity to learn that. Yes, question.
So you don't have to go too in detail, but why aren't these other representations realized in nature?
Nobody really knows. Nobody's been able to write down field theories that describe these representations, that describe particles that live in these representations. People have tried. It certainly is plausible that they might not appear in sort of the standard model of particle physics, but might appear in some other sort of system, some material system or something like that. There are, for example, lots of cases of particles that don't appear in sort of elementary particle physics, but do appear in condensed matter physics. We'll meet one of them by the end of class today, possibly. Yes?
What's the group ISO 31?
Oh, that's just a fancy name for the Poincare group. So the group of symmetries of special relativity. Sorry, I introduced that sort of terminology last class, but I'll just call it the Poincare group. But you will see that mathematical terminology somewhere. So yes, this is the possible list of particles that you can have in a theory of quantum mechanics plus special relativity. The interesting thing here is no fields were harmed in the making of this theorem, right? All I did is I said there's a Hilbert space, there's a set of unitary operators with a symmetry. I didn't say that there were fields, okay? I didn't say that we construct the Hilbert space using harmonic oscillators, blah, blah, blah. This is a completely general result that only assumes quantum mechanics and special relativity. Good stuff. Any other questions? Good. So what are the representations of the Lorentz group? Well, I wrote down for you last time the algebra of the Lorentz transformations. What I want to do is just tell you how we can actually rewrite that algebra a little bit in a way which will make it much more familiar. I won't go through all of the computational details because you'll do a lot of them on the problem set that I just handed out. But the basic idea is very straightforward. So the idea is that instead of working with the generators J mu nu that I described above, let's use some things that we understand a bit more physically. So let's let Ji be 1/2 epsilon I jk, j jk. Okay. So those would be the generators of rotations. So Ji is the generator of rotations about the I-axis, just as we reviewed sort of last time. And let's let Ki be J0I. So this is the Lorentz transformation that mixes time, x0, with xi. Okay. So this is the generator of a boost in the xi direction. And then so this is now a sort of, well, then it's sort of a straightforward exercise to go ahead and rewrite the algebra of Lorentz transformations in terms of these j's and k's. So I'll let you do that on your problem set. But instead what I want to do is I want to do a sort of dirty trick. What I want to do is consider a complex linear combination of these guys. So remember that the generators of a symmetry are usually taken to be Hermitian operators. But here I'm including a factor of I, so the n's are not Hermitian operators. So that, for example, ni dagger is not just ni, but differs from it in the sign of that second component. And then the algebra of Lorentz transformations, that is to say, the commutation relations of the generators of Lorentz transformations, takes a very simple form when you write it in terms of these n's. In particular, it just becomes 2 copies of the SU2 rotation symmetry. The n's obey the rotation algebra, and the n daggers obey the rotation algebra. So in fact, it's not just that the Lorentz group looks a little bit like the rotation group. The Lorentz group is nothing more, nothing less than 2 copies of the Lorentz group, of the rotation group. So the Lorentz algebra, or the Lorentz group, the set of Lorentz transformations, can be regarded as 2 copies of the rotation group, which is usually referred to as SU2. So mathematically, remember the name that we gave to the Lorentz group was SO3, 1. So the mathematical statement is that SO3, 1 is SU2 times SU2, where those 2 SU2s refer to the SU2 algebra generated by the n's and by the n daggers, respectively. So we often use a little bit of terminology when we describe the Lorentz transformations in this way. We distinguish between those 2 copies of the rotation group by calling one of them the right-handed rotations and the left-handed rotations, or the SU2 right and SU2 left. So we call them left and right. And for example, you will often see the states of different particles described in terms of how they behave under SU2 left or SU2 right. So for example, when people use the terminology helicity and say that a particle has a certain helicity or chirality, they're talking about how it transforms under the right or the left copy of SU2. Okay, so that's something that we'll return to a bit later on in this course. Yes?
Is that left or right copy specific to the dagger or dagger?
Yes, so SU2 right is generated by the NIs, and SU2 left is generated by the NI daggers. Absolutely. Unless I've exchanged, I can't really tell right from left, so, you know, that's a sort of convention, I suppose. Now, you already know what the representations of SU2 are. And if you don't, you'll know by tomorrow when you finish your problem set. And so we know what the representations of SU2 are. And so that means we know what the representations of the Lorentz group are. That means that a representation of the Lorentz group is given by a pair of representations of SU2. Now, I understand that I'm using a bit of a mathematical language. I'm talking about representations and products of groups and stuff like that, which is a little new to you. Don't worry. I'm going to do about 10 more minutes of using this mathematical language, and then I'll get very, very down to earth and tell you explicitly how everything looks in terms of vectors and matrices and stuff like that. Okay? So don't get too upset by the language. So remember, what are the representations of SU2? Okay. Well, there's one representation of SU2 for every natural number. So, for example, there's the spin 0 representation, which often is referred to as the 1 of SU2. We hear 1 refers to the dimension of the representation. Okay. So it's in the mathematical language of Hilbert spaces or vector spaces, is a one-dimensional vector space, and the generators of SU2 are represented by 1 matrices, each of which is 0, so that all the rotations are just 1. The rotations found by exponentiating 0 are just 1. There's also a spin 1/2 representation, referred to as the 2 of SU2. Why is it called the 2? It's called the 2 because it's a two-dimensional vector space, and the generators of that are the Pauli matrices, which are 2x2 matrices. There's a spin 1, which we won't really have too much time to discuss, at least not in the near future, called the 3, and so on and so forth. Now, typically, when you're talking about group representations, you often label a representation by the dimension of the vector space. So if you're representing a group by n matrices, you'll call that the n-dimensional representation of that group, or just the n of that group. In the case of SU2, I could equally well call them spin 0, spin 1/2, something like spin 1, stuff like that. Next semester, when we talk about quarks and gluons and all that stuff, there'll be a more complicated group that will make an appearance, SU3. And there, you can't really think about the representations in terms of spin 1/2, something like that. And so we just label them by the numbers. So for example, we'll say that the quarks live in the 3, or the 3 bar of SU3. And the gluons live in the 8 of SU3, stuff like that. So that means that a representation of the Lorentz group is given by a pair of integers that we could call n left and n right. So here, this number here refers is the n I'm referring to. So, for example, what is the 1, 1 representation of SU2, of the Lorentz group? Well, it's spin 0 on the left and spin 0 on the right. Okay. So that is just the usual scalar field that we've already met. It's a one-dimensional representation, so it's one number. The field is just one number per point in space-time. And if you wanted to work out explicitly what those matrices M are that we described above, how would you do it? Well, you would start by finding the matrices that describe the SU2 left and the SU2 right, and then you would set those equal to n here and n dagger. And then you would generate a finite Lorentz, you could go back into the original basis of the J mu nus, and then you could exponentiate those to get a finite Lorentz transformation. So there are two other, the next simplest representations have dimension, are given by the spin 1/2 for one of the SU2s and the trivial representation for the other SU2. So these are known as Weyl spinners. So this is referred to as the left-handed Weyl spinner, and this is referred to as the right-handed Weyl spinner. Interestingly enough, these representations don't occur in elementary particle physics, but they do occur in nature. They were only discovered last year, not in particle physics, but in condensed matter physics, where it turns out there's a material called a Weyl metal, okay, W-E-Y-L metal, not V-I-L-E metal, a Weyl metal, and the phonons, or the elementary excitations of this metal, the analogs of the phonons for the scalar, for our lattice model of a scalar field, turn out to be Weyl spinners. And they're described by some field equation and some, in fact, it was only predicted in 2014 that this class of metals would have Weyl spinners as their particles. And it was finally observed, I think, last summer, or earlier this summer. The next sort of thing that you could consider would be a 2, 2 representation. So this would be a 4-dimensional representation, because 2 times 2 is 4. And does anyone have any idea what this representation might be? It's a 4 vector. So it's the 4 vector. It's actually a little non-trivial to show that. So again, remember, how would you, so I already told you how a 4 vector transforms under a Lorentz transformation. Okay, wrote it down for you up here. Did I? No, I guess I didn't write it down for you. But it transforms by multiplication by the matrix lambda mu nu. And so actually showing in this language that the 2, 2 is the 4 vector is kind of non-trivial. So you have 4 quantities. What you do, again, is you know what the 2-dimensional representation of SU2 looks like. So you write down a set of 4 quantities that transform by the action of the Pauli matrices, acting on, so 2 copies of the Pauli matrices, and then you build those into a 4-dimensional representation, and then you trace through, so those, the n's and the n daggers would be given by the Pauli matrices, and then you would trace through and rewrite that in terms of the action on that 4-component object, and you can show that it's a vector representation. I was going to assign that as a problem set. I decided it was a little too hard, but maybe next week, okay, after you get used to all of this stuff. Nothing, yeah, no, so don't give up. Don't give up. Okay. And it turns out that the spinners that we'll be studying primarily in this class, which are known as the Dirac spinners, is given by a pair of Weyl spinners So it's given by a left-handed and a right-handed vial spinner. So the particles that appear in nature, at least in elementary particle physics, are not an individual left-handed or a right-handed vial spinner, but rather they're given by a pair of these. So it's some sort of four-component object. So the field will be a four-component object. I don't want to call it a vector because it's not a vector in the sense of a four vector. I mean, it's a spinner. It's a four-component spinner, which we can view as a column vector, some sort of four-component column vector, and then using all of the machinery that I've introduced to you in class so far today, you could work out explicitly what the Lorentz transformations are acting on this four-component spinner. Now, I could do that if that was how I wanted to proceed, but instead it turns out there's a much, much simpler way of constructing this using a trick that's due to Dirac, which is why they named the spinners after him. It's one of the cases where they actually named something after the person who invented it, which is kind of unusual. So that's what I'm going to introduce now. And that's going to sort of bring this kind of formal mathematical discussion of the possible particles that we could have to a much more explicit kind of down-to-earth level. But before I do so, let me pause and see if there are any questions. Is this more or less comprehensible? I mean, I do realize using this formal language of representations in group theory is probably new. And so just to make you at ease, I'll tell you it's just not something that is really going to be emphasized in this course. Okay? So I'm not going to really need to come back to any of this stuff much later in this course. Okay? But I think it is kind of something that everyone should see. So just so you can be familiar with the language. Any questions? Okay. Good. Spinners. And unless I say otherwise in this class, a spinner means a Dirac spinner. Okay, so not one of those vial spinners that we described above. Although we will later on discuss the relationship with the vial spinners. And what is a Dirac spinner? A Dirac spinner is it's a field usually denoted psi, which has four components. So in the language that we used earlier, we would say it's a four-dimensional representation of the Poincare symmetries, or the Lorentz symmetries. But it's a four-component object, which if we wanted to, we could represent as some sort of four-component column vector. But I'm going to suppress the indices whenever I can. So for example, we're going to, by the end of class today, have all sorts of 4x4 matrices flying around and spinners flying around, four-component spinners flying around. And I want you to, but we're going to be suppressing all of the indices. So in your head, you're going to have to keep track of what object is a four-component spinner and what object is a 4x4 matrix that acts on that four-component spinner. And what object is a 4-component column vector that would get dotted into a 4-component spinner, and so on and so forth. Because if we don't do this, the notation gets incredibly cumbersome. And so once you get used to doing this, it is really pretty easy. But, and it's actually much easier than keeping track of the indices explicitly. But occasionally it will be useful. So occasionally we might denote this as, say, psi A, okay, where A is an index that runs from 1 up to 4. But the important thing to remember is that this index A, it's not the same as a mu index that, say, labels the 4 components of a vector or the 4 components of an energy momentum vector or something like that. It does not transform under Lorentz transformations in that way. Instead, it transforms under Lorentz transformations in a different way, which we're going to describe right now. So you should think of a Dirac spinner as the generalization of the 2-component spinners that you met in your quantum mechanics class, where you describe a spin 1/2 particle by a 2-component object. So this is some analogous 4-component object. And the basic slogan that you need to keep in mind is that in special relativity, the 2 components of a spinner get doubled to become 4 components. And we'll see very precisely how that works. Good. So in order to write down, so this field psi will transform under a Lorentz transformation as psi goes to m of lambda times psi, where M is some 4x4 matrix. And the goal is to write down a set of M's. And the strategy that we'll use is we'll first write down the infinitesimal generators, then we'll exponentiate them to find the generators of a finite Lorentz transformation. So that means that we seek 4x4 matrices that we could call S mu nu, which obey the algebra or the commutation relations of the Lorentz transformation. And then a finite Lorentz transformation is found by exponentiating that. I guess I usually label these with both upper indices, so I'll move those indices up. So here's the trick. This is Dirac's famous trick. The trick is that if you have 4 matrices called gamma mu, which obey what's known as the Clifford algebra, also known as the Dirac algebra, but Dirac invented a lot of algebras, so we'll call it the Clifford algebra. So the Clifford algebra says that the anti-commutator, gamma nu minus gamma mu, of 2 of the gamma matrices is twice the metric. So here, mu and nu label the 4 different matrices, and I'm suppressing 2 other indices here. So this gamma here is a 4x4 matrix. This gamma here is a 4x4 matrix. And if I wanted to be really precise, I should really write an identity matrix here, which is a 4x4 matrix. So really, if we didn't suppress those spinner indices, this would be an equation which had 4 different free indices, a mu and a nu index, as well as 2 spinner indices. So is it clear, the equation that I'm writing down here? If it's not clear, it'll be clear by the time you do the next problem set, but hopefully it's clear now. I'll write down explicitly what these matrices are in just a minute. But now on to the trick. So you find 4 matrices which obey this. And then it's an easy exercise to show. It's one of the easy exercises you'll do on the problem set. That if you just take the commutator of 2 of these matrices, then these commutators obey the Lorentz algebra. That's just some mucking around with commutators. So S mu nu is a commutator. You take the commutator of these 2 S mu nus, so a commutator of 2 commutators. You write it all out. You get a bunch of products. You use this Clifford algebra, and it's not hard to turn that to see that these obey the Lorentz algebra. So let's all sort of bring this down to earth. Okay. So for us, we will take the gamma matrices to be the following. So they'll be the following 4 by 4 matrices. So gamma 0 will be 0, 1, 1, 0. Where here, 0 and 1 are 2 by 2 matrices. So these are all 2 by 2 matrices. 0 is the 2 by 2 matrix, all of whose entries are 0. 1 is the 2 by 2 identity matrix. And gamma I will be the 4 by 4 matrix, which we can write in block 2 by 2 form as 0 Pauli matrix minus Pauli matrix 0. So that, for example, the generator of boosts is going to be S0I, so that's minus I over 2 times the commutator. So that's the commutator, I over 4, times the commutator of gamma 0 with gamma I. So even I can work out the commutator of 2 by 2 matrices, especially when one of them is just the identity matrix. It's going to be sigma I minus sigma I. Okay. And the generator of rotations is Sij. So that is going to be 1/2 epsilon ijk times, now you have to compute the commutator of 2 Pauli matrices. That's pretty easy. It's going to be sigma k 0, 0, sigma k. So you can see now that this is really 2 copies of the standard generator, the standard representation of the rotation group. So in your quantum mechanics class, when you study a spin 1/2 particle, you represent the rotation generators by Pauli matrices. And here, you're representing the rotation generator by 2 Pauli matrices. So this really hopefully makes it clear that these things are very closely related to the spin 1/2 particles that you study in quantum mechanics. So I've introduced for you a set of matrices that obey the Clifford algebra. And it turns out to be a fact, an interesting fact, but not one that we'll bother to prove. So I'll just quote it for you. That all possible matrices that obey the Clifford algebra can be written by some change of basis as these gamma matrices that I've written above. So they're all related by a change of basis to those above. Okay, I should specify 4 by 4 gamma matrices. So the above basis is known as the Weyl basis for the gamma matrices. But if you look in other textbooks, you will probably find other sorts of bases being used. I think this basis is very nice to use because the SIJs just take the usual form for the rotation generators. So you can make very clear the relationship of these spinors to the spinors that you met in your quantum mechanics classes. You know, you should be aware that other bases are sometimes used. They're useful for other reasons sometimes. Okay. Any questions? So just to bring this full circle and to make everything very explicit, under a Lorentz transformation, that is to say a change of coordinates where x goes to some x prime, which is lambda mu nu x nu, where lambda is e to the I omega mu nu times those generators j mu nu. How does our spinor transform? Well, our spinor is a field, so it's a set of 4 components, each of which is a function of space-time, and it transforms to some 4 by 4 matrix times the spinor, of course, evaluated now at the point x prime rather than x, where that 4 by 4 matrix, which I'll call lambda sub 1/2, to remind ourselves that it's the, so this is what I called m of lambda up above, but I'll just call it lambda sub 1/2 to remind ourselves that it's the Lorentz transformation written in the spin 1/2, or the spin 1/2 representation. It's the exponential of I omega mu nu times S mu nu, where S were those commutators of the gamma matrices that I wrote down above. So the goal then is to find a good set of equations of motion which can be obeyed by these Dirac spinors. One sort of simple equation of motion you could write would be the Klein-Gordon equation. Okay? So for example, I guess here, d mu plus m squared acting on psi is equal to 0. Okay? So that you could think of as an equation of motion for our field's side. That is a perfectly fine equation of motion. In particular, if psi obeys this equation of motion in one coordinate system, it will obey this equation of motion in any other coordinate system. Why? Well, we already saw that under a Lorentz transformation, that Klein-Gordon operator just goes to d mu prime plus m squared. And then we have a lambda to the 1/2 acting on psi. But lambda to the 1/2 is just a constant 4x4 matrix. So it doesn't talk, so, you know, you can just bring it to the other side of that operator right there. And moreover, it's an invertible matrix. Its determinant is not 0. So that means that if this is that you can just multiply this equation here by lambda to the 1/2 inverse. And you'll see that if this equation, the Klein-Gordon equation for a Dirac spinner, is equal to 0 in one reference frame, it's equal to 0 in any other reference frame. Just like, for example, a scalar field, the Klein-Gordon equation has this property for a scalar field. Or, as you learned in your electromagnetism class, the Maxwell's equations have this property. If they're satisfied in one frame of reference, they're satisfied in every other frame of reference. Indeed, the Dirac spinners that we'll study in this class, a free Dirac spinner, does obey the Klein-Gordon equation. But it turns out that it's possible to write down an even stronger equation of motion. In particular, it's possible to write down a first-order equation of motion rather than a second-order equation of motion. That's the thing that's really different about Dirac spinners relative to scalar fields. What is that equation of motion? Well, let me just write it down for you. So I times gamma mu d mu minus m acting on psi is equal to 0. So this is known as the Dirac equation. You may have encountered it in your quantum mechanics class. How many of you saw the Dirac equation in your quantum mechanics class? Okay. You probably did not see it written in this form in terms of gamma matrices. Did any of you see it written in terms of gamma matrices? You did. Okay. Usually you see it written in terms of matrices like alpha and beta. Is that what you guys saw? So often you see it written in terms of matrices called alpha and beta, which are just gamma matrices written in a slightly different form. The Dirac equation, as you usually see it in your quantum mechanics class, is viewed as an equation, for a quantum mechanical wave function in single particle quantum mechanics. It's important to remember that here, when I write down the Dirac equation, it's an equation that's satisfied by a classical field. So it's an equation for your classical degrees of freedom, in the same way that Maxwell's equations are your equations for classical degrees of freedom, the electromagnetic field strength. So what I want to do in the last few minutes is just check that indeed this quantity it is a good equations of motion, in the sense that if it's satisfied in one reference frame, it's satisfied in any other reference frame. And the key fact in proving this is that gamma mu, under a Lorentz transformation, transforms as a vector. What do I mean by that? Well, so gamma mu, so remember psi under a Lorentz transformation got multiplied by lambda to the 1/2. Gamma is a 4x4 matrix, not a vector, so it should transform by conjugation by this matrix lambda to the 1/2. And in particular, the claim, and this is something that is straightforward to verify, and you'll verify it infinitesimally on your problem set, is that if you conjugate your gamma mu matrix by lambda to the 1/2, what do you get? You get lambda mu nu, gamma nu. So in particular, if you do the coordinate transformation where x mu goes to lambda mu nu, x nu, and then you write down the corresponding matrix lambda to the 1/2 that tells you how spinors transform, and you conjugate gamma mu by that matrix, you get lambda mu nu gamma nu. So that says that we can treat, so roughly speaking, what that's telling us is that you can treat the mu index of gamma just like a vector index, which is a good thing. Otherwise, it would have been silly of me to name it mu. Right? So the proof follows really from the fact that you can do this infinitesimally. So infinitesimally, you can work this out and show that this, so the infinitesimal transformations are, so to describe the infinitesimal transformations, one needs to compute the commutator of gamma with S, okay, right? Because, here, let me write that a little bit more explicitly. So lambda to the 1/2 is e to the I omega mu nu, S mu nu. So that implies that lambda to the 1/2 inverse gamma mu lambda to the 1/2 is gamma mu plus I omega, let's call it rho sigma, times the commutator of gamma mu with S rho sigma, plus higher order terms in omega. Whereas, remember that lambda mu nu gamma nu is, if you were writing, remember lambda mu nu is e to the I omega mu nu times the 4x4 matrices J mu nu, which we wrote down last class. And you can show that this guy, so this is gamma mu nu plus I omega rho sigma well, it gets a little complicated if I write it this way. No, I guess it's fine. It's J rho sigma mu nu gamma nu plus dot dot dot. And so infinitesimally, so to show this infinitesimally, which you will do on your problem set, you just need to compute the commutator of these guys and show that it's given by this 4x4 matrix. Where, remember, this 4x4 matrix is the one that we worked out last time. It was delta rho, so J rho sigma alpha beta was I times delta rho alpha delta sigma beta minus delta rho beta delta sigma alpha. This is the 4x4 matrix whose entries are 1s or 0s that generate the Lorentz transformations. In the same, so for example, J 0, 1 is the 4x4 matrix that you get if you take the Lorentz transformation that mixes x and t and you work it out infinitesimally at small velocities or small rapidities. Okay. So that's the calculation we did last time. Okay, so the point is that gamma mu transforms as a 4 vector. So under a Lorentz transformation, how does the Dirac equation transform? Well, gamma mu d mu of psi, how does that transform? Well, d mu transforms like a vector under a Lorentz transformation. That's because d by dx mu prime is given by lambda mu nu, d by dx nu, so that's the chain rule for derivatives. And then we have lambda to the 1/2 times psi. And then, of course, we can, so remember, this is a 4 by 4 matrix, but this does not, but it commutes with that guy. It doesn't have any spinor indices. And so you can use you can rewrite this as, well, let's rewrite this as lambda to the 1/2, lambda to the 1/2 inverse, gamma mu lambda to the 1/2 times lambda mu nu d nu psi. Okay. So all I've done is I've introduced a factor of 1 there written in a particularly perverse way and moved that lambda 1/2 to the other side. I can now use this fact here, okay, that when you conjugate gamma by lambda to the 1/2, you get a Lorentz matrix. Okay. So that is lambda to the 1/2 times this conjugation here, which we could write as gamma alpha lambda alpha mu, and then we get this term here, lambda mu nu d nu psi. And then what is this here? Well, by the definition of a Lorentz transformation, remember a Lorentz transformation is, you multiply 2 lambdas together and you get a metric, right? So this is delta alpha nu. That's the definition of a Lorentz transformation. So this is lambda to the 1/2 gamma alpha d alpha psi. Okay. So what does that mean? And remember, lambda to the 1/2 is an invertible matrix. So that means that the Dirac equation has the property that if it's satisfied in one reference frame, it is satisfied in all reference frames. And that's the proof of what we would say, not Lorentz invariance, but we would call it Lorentz covariance of the Dirac equation. We would call it covariance rather than invariance because you get this factor of lambda to the 1/2 out front. And the Dirac equation is the classical equation of motion of a spin 1/2 field of mass m. And just to recapitulate, psi here is a 4-component object, so it's a 4-component spinor, and gamma here is a 4 by 4 matrix. Now so this is where I wanted to end, but just for my information, so those of you, raise your hand, how many of you have seen this in your quantum mechanics class? Raise your hand high so I can see. Okay, about half, a little more than half. Those of you who have seen it, did you see, I'm trying to decide whether I should go through the treatment of the Dirac equation as an equation for a wave function in single particle quantum mechanics. So that leads you to the notion of a Dirac sea, and it's a different way of thinking about particle creation and annihilation. Have you seen the Dirac sea? S-E-A. How many? Raise your hand if you've seen the Dirac sea, kind of. I mean, I might do it. Would you like me to do that? It's a very interesting way of, it's kind of not in the main direction of things that we need to do in this class, but it is a very interesting and different way of thinking about particle creation and destruction in quantum mechanics. Should I do that? I don't know. I haven't decided. I mean, have any of you seen the prediction of the anomalous magnetic moment of the electron from the Dirac equation? That's kind of like the signature success of the classical Dirac equation. We're going to do that because, well, the whole point of quantum electrodynamics is that you then predict the first correction to that. So that's certainly something that we'll do. But if I can, maybe what I'll do is I'll spend a little bit of time discussing the interpretation of the Dirac equation as an equation of as a quantum wave equation as well. Okay. The only reason I'm hesitant to do that is that the Dirac equation is not a quantum wave equation. Okay. It's a classical equation of motion like Maxwell's equation. Okay. And so sometimes people get confused and mistake the Dirac equation for a quantum wave equation. If you do that, there's an interesting physical interpretation, which I guess I'll go through. But you really, every time I do that, you just need to repeat to yourself into your head, the Dirac equation is not a quantum wave equation. The Dirac equation is not a quantum wave equation. You keep saying that to yourself until you believe that. But it is interesting to interpret it as a quantum wave equation. Good. Any other questions? No questions. Yes.
So, about the regular theorem,
Yes.
when you said that, so a particle is a irreducible representation of the Poincare group, but then you start labeling the particles
Yes.
as a representation of the Lorentz group.
Mhm.
So does it hold
Uh,
true also for the Poincare group?
It does, yeah. The reason why we often talk about the Lorentz group is because that's the kind of non-trivial piece, right? How do these things transform under Poincare? Yeah, I mean, under Poincare, well, what do? We would, and we're going to do this very explicitly. So how would this psi, for example, transform under Poincare? Well, you would write it in a basis of plane waves, and a mode with momentum k will get multiplied by a phase factor when you do a translation, just like for a scalar field. So the reason, so we often only focus on the Lorentz transformations because that's the kind of tricky part. But you should always keep in mind that there are the translation generators too. And so, for example, you can reasonably easily verify that this equation of motion that I've written down is translation invariant. Okay. In particular, how does psi transform under a translation? Well, it doesn't get multiplied by a matrix at all. Okay. Right. It just gets, under a translation, psi of x goes to psi of x plus a, which is e to the, what did we call it? I a mu p mu psi of x, where again p mu is that differential operator d by dx mu. And then you can easily check, and then the fact that this equation of motion is translation invariant is pretty easy to see. It's just the statement that d by d, that this operator here commutes with the generator of translations. Right. So just as the fact that the Hamiltonian is p squared plus m squared, or p squared plus m squared is translation invariant because it commutes with p. So here we have, an analog of that where you have gamma dot p commutes with p. So, yeah. So if that's not entirely clear, I encourage you to check for yourself that this equation of motion is translation invariant. And while you're at it, check that the Klein-Gordon equation is translation invariant. That is to say, if you take the Klein-Gordon equation for a field phi of x, do the change of coordinates where x prime is x plus a, and write the Klein-Gordon equation in the x prime coordinates, you get exactly the same Klein-Gordon equation back again. In particular, d by dx is the same as d by dx prime, so there's not very much to do here. There's also not very much to do in this case as well. So it is, we often talk about, I often just talk about Lorentz invariance, not Poincare invariance, just because it's the sort of tricky part. Good question. Other questions? Good. Okay, see you next week.